Questions about anything from last time? No? Well, today's a kind of a fun fact. I'm going to explore this thing called the monotone convergence theorem. Oh, by the way, I have to cancel my office hour on Tuesday. But if you put your questions on Piazza, I will answer them there. So I prefer you don't use the private question on Piazza because the idea of Piazza is my answer, so I don't have to repeat it. Usually if you have a question, there's nothing to be embarrassed about. Lots of people probably have the same question. And if you are embarrassed, you can post it anonymously. Anyway, it's probably good if the whole class sees your question and sees my answer. Also, you're welcome to answer each other. In fact, I should be encouraging more of that on Piazza because that makes it much better when you start answering each other's questions, especially after hours. So let's see, today's subject is about monotone sequences. And this first one I put down, let's see, this famous theorem, the monotone convergence theorem. I remember it as a fact about increasing sequences. Of course, anything that's true for increasing sequences would have a version for decreasing sequences. Anyway, for increasing sequences, this fact says if we have an increasing sequence, meaning it's getting bigger and bigger, and it's bounded from above, then it must converge. And in fact, it's going to be easy to see that it converges to the supremum of the sequence, the least upper bound. That's the version some books would, if they don't call it the monotone convergence theorem, that's the theorem they're referring to. And of course, there's the decreasing version is that if it's bounded from below and it's decreasing, then it would have a limit, and it would be the infimum. So our book defines a sequence such that x1 is less than or equal to x2, is less than or equal to x3, etc., etc. They call that increasing. Some books would call that non-decreasing because less than or equal to is not greater than. So it's not non-decreasing, yeah. But the book likes increasing, and that's a common thing. Lots of books do that too, so it's kind of normal. And if the first one's bigger than the second one, greater or equal to, etc., it's called decreasing. And notice the greater or equal to means you could sit around for a while and stay the same before you start descending again. In fact, they all could be equal. That would be a decreasing sequence. So a graph here would be, we'd have x1, x2, and then maybe x3 is the same as x2. That would be okay. But it can't go less, so it's non-decreasing. And then x4, etc., x5, and maybe x6 would be the same as x5, etc. And of course, I could make a sequence that goes shooting off to the infinity, like the integers would be an increasing sequence. But it certainly wouldn't be a bounded from above. So there'd be some barrier on the right that they can't pass. So they'd have an upper bound. And then if you start trying to draw a picture of that, you see they get jammed up and they start gobbing up someplace. And the place they gob up is going to be the supremum, the least upper bound. So some books some books would call increasing, they would call that non-decreasing. That's kind of a mouthful, and nobody likes to think like that. And decreasing would be non-increasing. Also, sometimes I like to talk about strictly increasing and strictly decreasing. So those words, if I use them especially, strictly increasing, I would use strict inequalities in place of the less than or equal. Similar for decreasing, etc. Questions about that? So those are the words today. And so let me mention that theorem. This is the one thing I'm actually going to demonstrate today. Number one, if xn is increasing, sequence that is bounded from above then it has a limit. Then the limit as n goes to infinity of xn exists and is equal to the supremum. Stepper bound is the same as the supremum of the terms. And the version, similar version for decreasing is that if xn is decreasing and bounded from below, from below, then the limit of the xn's is equal to the infimum of the terms. Okay. And of course, if you can prove one, you can prove the other just by taking minuses of the terms. You can flip a sequence from being increasing to decreasing when you take minus the terms. So I'll only prove one of these because it's a fairly routine thing to see that they're equivalent. Let's see, I should have defined another word. Monotone means increasing or decreasing. Definition. Monotone means increasing or decreasing. Going in one direction, in other words. And so oh, by the way, when the sequence, let's say it's increasing. Being bounded above from it is cool, but x1 is a bound from the left. So an increasing sequence is always bounded below. And a decreasing sequence is always bounded from above. So you don't have to worry about the other end being bounded. That would always be a consequence of the definition. So a summary of this theorem is monotone. A monotone sequence is convergent if and only if it's bounded. I guess that's what's referred to as the monotone convergence theorem. Sequence is convergent if and only if it is bounded. And for an increasing sequence, that the relevant side would be the above side. And for a decreasing sequence, the relevant side would be the below side. Okay, so now I want to demonstrate this one thing today. Proof of number 1 of the theorem. Let's suppose we have an increasing sequence that's bounded above. Is increasing and bounded above. That means it has an upper bound. So of course it has a least upper bound. It has an upper bound. So it has a least one. And of course that's the definition of the soup. That's the soup of the xn's. Let L be equal to the soup. Okay, I'm going to show, of course, that the series converges to L. And here's the picture. Okay, so let's see, how do you show that something converges? You got to let epsilon be any positive number. So start with an epsilon bigger than 0. Doesn't matter how small it is. And now my x's, x1 is less than or equal to x2, is less than or equal to x3, maybe x4 is the same, x5, etc. And L is over here as a barrier. That's the least upper bound. Okay. These x's are getting bigger and bigger, and I'm claiming they're piling up at L. They gotta get bigger and bigger. Sometimes they might stay the same, but they get pretty crowded. And if you ask yourself, how am I going to fit infinitely many in there, you realize they're going to gunk up and pile up someplace if you start drawing pictures and thinking about it. But from the definition of limit, I need to take an epsilon bigger than 0, and let's think about, I'll stick my epsilon right here. Let's make this be L minus epsilon. Okay, I claim that the red dots have to sneak into that set. Okay? And so here's what I claim. There has to be a red dot inside there. There is an xn. This is kind of giving you a big hint. There is an xn, I'll call it x sub capital N, in L minus epsilon to L. And that's pretty clear, because if not, If not, that means xn would be less than or equal to L minus epsilon for all n. And that's a big oops. That would mean that L minus epsilon would be an upper bound. So L minus epsilon would be an upper bound. For the terms. But L minus epsilon is less than L, and L was the least upper bound. I'm kind of beating this to death, but it's worth doing it that way in the beginning. And that is a contradiction. Lightning bolt. So my claim is correct. There is an xn in there. And because the sequence is increasing, from xn on, they're all in there. So there exists an xn in the interval from L minus epsilon to L. Ask yourself why I'm making a closed bracket on the right. It is possible that the whole sequence is equal to L. That would be a weird case. So I have to make it possible that they all be L. Let's just see, there's an xn in there. So the aha moment is, from that moment on, they're all in there. Since xn is less than or equal to xn plus 1 is less than or equal to xn plus 2 is less than or equal to dot, 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 and they're all less than or equal to L, we see that from that point on, all those terms are in there. So we see that xn minus L, let's see, that would be equal to, the absolute value of xn minus L would be equal to, since L is bigger than all of them, L minus xn. And that would be strictly less than epsilon, because I showed you that it's in that thing, for n bigger than or equal to capital N. So check. That's what we wanted to see. I just showed you the limit exists and is what it should, it's L. About that one? That's an important argument to understand backwards and forwards. I guess I should write that remark. Remark. An increasing in sequence is bounded on from below by the first term. We don't have to think about that end. So it's bounded below by x1. A decreasing sequence is bounded above by x1. Decreasing. Bounded. Did I say? I meant above. A decreasing sequence is bounded above by x1. Oh, I want to do some fun examples today. Here's an example. This one isn't a fun one yet. This 1 over the square root of n from 1 to infinity. Let's see. That's going to be easy to analyze from this point of view because, I mean, we could analyze it. We kind of did analyze it the last time. But now we have this theorem at our disposal. So notice that we know that the 1 over 1 is greater than 1 over 2 is greater than 1 over 3. Let's see. I'll be a baby about this. 1 is less than 2 is less than 3, etc. So 1 over 1 is greater than 1 over 2 is greater than 1 over 3 is greater than ... And so the square root of 1 over 1 is greater than, these are all positive, so the square roots would have this same property, greater than ... So we see that that's a decreasing sequence. In fact, it's strictly decreasing. So this is a strictly sequence. And they're all positive, so they're bounded below by 0. And so the limit exists and is equal to the nth by the monotone convergence theorem. It's equal to 0, which is the nth of 1 over the square root of n. And let's see, if I wanted to prove that the nth is 0, I might do it this way. So remark, given epsilon bigger than 0, there exists a capital N such that capital N is bigger than epsilon squared, which means that 1 over n is less than, oops, not epsilon squared, 1 over epsilon squared. I'm cheating now. I'll tell you why I'm cheating. So 1 over n would be less than epsilon squared. And so 1 over the square root of n would be less than epsilon. And so they get arbitrarily small. Actually, I just proved that the thing converges to 0. But the reason I did this is kind of the argument I skipped when I said, oh, if x equals 0 and that square root thing was 0, then it was easy. This is exactly why it would be easy. And I also did something sleazy here. If I was going to explain this properly, I would have started with the bottom inequality and worked backwards to see what I needed in the beginning. Of course, this is the Archimedean property. So it goes back to a couple chapters ago. So yeah, if I wanted that bottom last inequality, I'd write it down and then go backwards and see, here's what I need. And that certainly is true. And then that would be the capital N that works for epsilon. Okay, now the thing I promised that was going to be fun. I want to think about a famous thing called Newton's method. And I'll do it for the square root of 2, since we've been obsessed with the square root of 2 for a while. Newton's method for computing the square root of 2. It's a beautiful thing. It used to be, we used to teach it in freshman calculus. I'm not sure we do anymore. Did you see it in freshman calculus? You'll notice. So let's see, what is Newton's method? It's we graph x squared minus 2. So this is a graph of x squared minus 2. Looks like that. And x squared minus 2 crosses the positive real axis, where x is the square root of 2. So that red dot is the square root of 2. And my first guess for this, I don't know what the square root of 2 is. I want to calculate it numerically. I don't know what it is. My first guess is going to be, well, let's try 2. Well, you calculate x2 squared is 4. That's too big. And so I want to improve my guess, and Newton's brilliant idea was, okay, slide in along the tangent vector. And here's an improved guess. That one's too big too, because this thing is bulging out. It's concave up, so it's going to peel off the actual curve and hit the x-axis before it gets to the square root of 2. And I keep repeating this process. Get another improved guess, and when I square that, it's too big. And my next improved guess, I would follow the tangent vector again. So that's Newton's method. Take a guess, realize it's wrong, slide in along the tangent vector and get a new guess. It's still wrong, but it's closer. And in fact, they get closer and closer, and they're a decreasing sequence that's bounded below. And so they do have a limit. All right? So the aha moment here is, this is a bounded sequence. What is it? It's a decreasing sequence. It's actually strictly decreasing. It's pretty easy to see that it's bounded below. It's actually bounded below by the square root of 2, but certainly bounded below by 1. And so it has a limit. And I'm going to show you that the limit, I'm going to claim the limit is the square root of 2. And if you had to calculate square root of 2 numerically with your bare hands, this would spit it out real nicely. And real fast, too. Okay, so now let me demonstrate this fact. Okay, so let's see what... I'll magnify my thing here. And I'll make it bulge out more. I want it to bulge more. Okay, so here's going to be an x. That's one of my things that I guess. Let's write f of x equals x squared minus 2. Okay, so that triangle, this side here is f of xn. And now Newton's method says, okay, that's my guess, or my idea for my approximate answer. To get a better answer, I'm going to follow the tangent line. It didn't work. This is a tangent line. And of course, being a tangent line, its slope is going to be equal to f prime of xn. That should look like a straight line. And now my improved guess is going to be this one. So that'll be my next thing, and it's going to be the improved guess. Okay, and so I have a picture there, and I have a rise of a run and a slope. So it's very simple to write down what you see there. The aha that Newton must have had is that the slope is equal to the rise over the run. The rise is f of xn. The run is xn minus xn plus 1. And so I can solve that for xn plus 1. Let me mess around with it for a minute. Let's see. I'll put the xn minus xn minus 1 over here, and I'll write over here that's f of xn over f prime of xn. That's f of xn. Let's see. F of xn is xn squared minus 2 over 2xn. That's positive. And so this is a decreasing sequence. So this is greater than or equal to 0. And so this shows that the xn's are decreasing. And you can fiddle, it takes some fiddling around with inequalities to see that they're all bigger than, say, 1. So I'm not going to show this. So play around with inequalities. And then induction. The book goes into some of these details, but I don't want to blow a whole lot of time doing them. So play around with inequalities. And induction. To see that all the xn's are greater than 1. In fact, all the xn's, their xn squared would be greater than 2. So, so let's see. To see all the xn squareds are actually greater than 2. That's kind of a thing I'm skipping here today. So xn squared is greater or equal to 2. And so for all n, so the xn's are bigger than 1 for all n2. So that series is bounded below by 1. And so it has a limit. Let's see, I should put this in a box. Mess around with this for a second. Newton's formula. Solve that red box for xn plus 1. And it tells me that xn plus 1 you get from xn by subtracting f of xn over f prime of xn. Pretty simple algorithm. You spit out one new one from the old one. And when you write that out, let's see, in our case, that would be equal xn minus xn squared minus 2 over 2xn is the derivative. And when you clean that up, you get 1/2 xn plus 1 over x. What? One half xn plus 1 over xn. That's the thing you mess around with and show that those are all bigger than 1. They're decreasing, etc. But now that I have that formula, so I'll put this in a red box. That was the general formula, but for this particular thing, you can find the zeros of any function this way. That's the formula for our particular case. And here's the cool thing to do. We know these xn's converge. As n goes to infinity. Well, if xn goes to L, then of course xn plus n plus 1 also goes to L. So also xn plus 1 goes to L as n goes to infinity. It's even farther out along the tail end. So I would say that's a duh kind of thing. And so when you look at that red box and take limits, take limits in the red box. Okay, I'll do it. I'll write it out again. Xn plus 1 equals 1/2 xn plus 1 over xn. This is going to go to L. This is going to go to 1/2 L. And this one's going to go to 1 over L. It's important to point out that L can't be 0. Those are all, they're all bigger than or equal to 1. So the limit certainly can't be 0. So we know that L is bigger than or equal to 1. So it's not 0. And so I know that the limit of the 1 over it is 1 over the limit. Ugh. Did I make a mistake? Oh, no, I didn't make a mistake. Let's see, what am I getting here? I'll subtract the 1/2 L, and I get 1/2 L equals 1 over L. And therefore, L squared equals 2. Bingo. I found the square root of 2. And there's some fun couple sentences in the book that show you how you could determine, let's say you wanted to get the square root of 2 up to 10 decimal places. There's a way to look at those formulas and figure out, yes, I've reached that point, and now I have the square root of 2 guaranteed within 10 decimal places. That's a fun thing to think about. So this is really a genuine, efficient way to calculate the square root of 2. And notice this little trick here of having a recursion formula that you slide limits in. That's a standard way to find what the limit is actually going to be, and it is what you want it to be. Questions about that? That's fun. Yeah.
Are we allowed to use derivatives?
No. No. The book said, actually the book uses this formula, So the question was, can you use derivatives? They're there, and you should think about derivatives. But when you do the homework, you wouldn't need to use them. Here's what the book did to avoid talking about derivatives in Newton's method. This formula apparently was known to the ancient Babylonians. And they didn't, I don't know how they got it without thinking about Newton's method, but they somehow understood this iterative formula. And so that formula has existed for a long time. And so the book just pulls it out of thin air, kind of. I like to motivate it with Newton's method, because it's a beautiful thing to think about. So that's my goal in this class, is to really enrich the lecture, make it easier to read, and maybe more fun. Another thing the book did today in this lesson, which is kind of fascinating, it looked at the very famous series 1 plus 1 over n to the n. This is a series you would use, this is a thing you'd use if you were studying compound interest. You've probably seen it in freshman calculus and maybe even in high school. That's a famous series that converges to e as n goes to infinity. E of the exponential function. Either that or it stands for Euler. I never was quite sure. And so the book shows that this is an increasing sequence. 1 over n to the n is an increasing sequence. Bounded above by something easy like 3. So it converges, and in fact, you could define the limit of that sequence to be e. Okay, so here's how the book does this. Let's see, there's the famous binomial theorem that you could by mathematical induction, which says that a plus b to the n is the sum as k goes from 0 to n of n choose k, a to the k, e to the n minus k. The n choose k's you can get by Pascal's triangle. So let's see, n choose k is n factorial over n minus k factorial times k factorial. And so the book takes 1 plus 1 over n to the n and uses the binomial theorem and gets that it's, what do they get? Sum as k goes from 0 to n of n factorial over n minus k factorial times k factorial times 1 over n to the k. Yes. That. So that's what you get when you plug in use the binomial theorem. And then the book cleverly writes it out for n plus 1 and pairs terms in clever ways and compares them. And it's murder. I mean, it's not murder. What bore you to death if I tried to write it all out here. But the book does it very efficiently and cleanly, and you look at it and you say, oh yeah, I would have thought of that in about 10 years. That's the thing about math. People think about this stuff all the time, and eventually somebody has a brilliant idea and it shows up in a book, and so it's always getting easier and better. And so you can show that that's strictly less than. So the book cleverly splits this up. One over 1 plus n to the n, and 1 over 1 plus n plus 1 to the n plus 1, and shows that they're getting strictly bigger. One over 1 plus n to the n is strictly less than 1 plus 1 over n plus 1 to the n plus 1. And then an induction shows that they're all less than 3. Start out with the first one being less than 3, and then you can show that they're all less than 3. Yeah. Anyway, it's work. And so I wanted to, in the last couple of minutes when you're tired of watching me do inequalities, how did you do this in freshman calculus? Let's see, here's what you did. You said n plus 1 over n, 1 plus 1 over n to the n is e to the log of that. And then you see that thing inside the exponential, the log of 1 plus 1 over n to the n is equal to n log 1 plus 1 over n. And there, I want to put, that's not in the form of a L'Hopital's indeterminate form. So I'll put that log 1 plus 1 over n on the top, and I'll put 1 over n on the bottom. As 1 over n goes to, as n goes to infinity, 1 over n goes to 0. So that top thing is going to be log of 1, which is 0. So this is a 0 over 0 indeterminate form. And so you're not allowed to use this, but this is what you did in freshman calculus. This goes to the limit of the derivative as n goes to infinity. And the derivative of the thing on the top would be 1 over 1 plus 1 over n times the derivative of that thing, which is minus 1 over n squared, the denominator that is. And the derivative of this denominator would be minus 1 over n squared. They cancel, and then you get that that's the limit of something simple. 1 over 1 plus 1 over n. And 1 over n goes to 0, so that's 1 over 1. That's going to be 1 over 1 plus 0 equals 1. So that thing inside the exponential is sliding to 1. So the aha moment is 1 plus 1 over n to the n is sliding into 1. The log of it is, what did I say? Yeah, the natural log of that I just showed you is sliding into 1. And the exponential function is continuous. These are all words that are off limits, but you obviously know them. It's continuous at x equal 1. So